method, which is the method of sections. Previously, we discussed the method of joins. In the methods of joins, we are going to say that since the truss is in equilibrium, it means the joints, each and every joint is going to be in equilibrium. Then we are going to draw the free body diagram for the joints, and then we are going to apply the equations of equilibrium for similarly to the equilibrium of a particle. Summation of the forces in x-axis should equal 0, and the forces in the y-axis should equal 0. So here we are going to learn other method. This one, it has its own advantage. I can know the forces acting on the member in the middle or at any location in the truss. Not like the the method of joints. So the principle here, it says that also since the body is in equilibrium, that means any part of the body is going to be in equilibrium as well. So for example, here we have a member subjected to tension. So I have tension forces is going to be acting away from the member. The force here is going to pull away from the member, and the force here is going to pull away from the member. Then if I are going to apply a section here or pass a section here, I'm going to separate that member into two members. Then if you are going to do that, and if you want to maintain the equilibrium, then you are going to see the internal forces. And in that case, I'm not going to have any shear or any moment, because I have only the force which is in that direction. So in that case, I'm going to have internal forces, which is the axial force here and the axial force there. It means that at that location, I'll be able to know the forces acting on the member. So if this one is in equilibrium, if I make a cut here, then this part also is going to be in equilibrium, and this part also is going to be in equilibrium. But I need to put the internal forces. Similarly, if I have a member with compression, we know that in the case of the compression, the force is going to push towards the member. So pushing toward the members here and pushing toward the members there. Since this member is in equilibrium, if I'm going to pass a section here, then this part is going to be in equilibrium if I'm going to put the internal forces. And similarly here, this part is going to be in equilibrium if I'm going to put the internal forces. And we use that method in order to know the internal forces in the beam. I need to pass a section at the point of interest, and then I need to put the internal forces with the positive senses. So here, since we have a truss and the truss is in equilibrium, it means that if I'm going to cut here, that means that part is going to be in equilibrium, and that part is going to be in equilibrium as well. But I need to put the internal forces. So the first step to use the method of the section, I need to pass a section at the required members. So if I'm going to know, for example, it's required to know the forces acting on the member BC and GC and FB, I'm going to cut here. Because when I cut here, I'm going to see the internal forces acting on this member and that member and that member. So I need to pass a section, then I'm going to end up with two parts. I'm going to have the left part and the right part. So I need to isolate the two parts of the truss, separated by the cut section. We cut here, and then we need to draw the free body diagram for the left part and for the right part. Like I said here, in the truss, we are going to have only normal force, no shear force, no moment. Because if you do remember the assumptions, we say that all the forces are going to be applied to the joints And also, we said that the members are connected together at smooth pin. That means I'm not going to have any shear force or the moment. So I'm going to have only normal forces. So when I cut here, I'm going to have normal forces. When I cut here, I'm going to have normal forces. The normal forces is perpendicular to the cross section. So if the cross section is here, it's going to be perpendicular to the cross section. If the cross section like that, is going to be perpendicular to the cross section. And similarly here. Then what about the direction? Again, if you are going to say that direction is pulling away from the members, it's mean here we have tension. Again, if it's pulling away from the member, it's mean that I have tension here. If it's pushing toward the member, it's mean that I have compression. So I have the choice in order to choose whatever direction. Because when you are going to find out the answers, if the answer came out to be negative, that means your assumption is incorrect. We have done this a lot throughout that course. Also, similarly, I need to put the internal forces on the right part. Of course, the direction there is going to be opposite. If the direction here is like that, here is also going to be opposite to that one, because we say that they are acting on the same point. According to Newton's third law, the forces should equal 0. So now I need to choose either the left part or the right part. So if I'm going to use the left part, now I'm in position in order to apply the equations of the equilibrium. Summation of the forces in the x-axis should equal 0. The forces in the y-axis should equal 0. And the moment about any point should equal 0. Now I need to choose either the left part or the right part. So here, if I'm going to use or to choose the left part, then I don't have any unknown forces. But if I'm going to choose the right part, here I have unknown forces. So here I have unknown forces. I have the support reactions here and the support reaction there. If I'm going to choose the right part, I need to determine the support reactions. If I'm going to choose the right part here, the left part, I don't need to use the calculate the support reaction. So the best choice here is to choose the right part. Then you are going to use the equations of equilibrium for this case here. Then if I'm going to apply the equations of equilibrium, I will be able to determine the member forces at the cut section. I'll be able to know FBC and FGC and FGF, whether you used the left part or the right part. We have some points we need to take care of it. Then if you are going to, for example, know the forces here, I need to cut it here. So for example, if it's required to know the forces for this member, and that member, I'm going to cut here. And I'm going to have the left part and the right part. If it's required to calculate the forces here in this member AB and AE, I need to cut here. I'm going to have left part and right part. It depends on the questions. So we have very important notes. You need to take care of it. The first note is try to select a cut section that passes through not more than 3 members in which the forces are unknown. So for example, if I'm going to cut here, then I'm going to have 3 unknown forces here and here and here. If I'm going to cut and then I'm going to end up with more than 3 unknowns, here, then since I have only 3 equations of equilibrium, it's going to be very difficult to solve the problem. So make sure that the place where you are going to make the cut, make sure that you are going to have maximum 3 unknown forces. So it's very important. Note Also, before isolating the appropriate section, for example, you are going to cut here. So before you are going to make the cut and put the internal forces, make sure that you can analyze the section without getting the support reaction. For example, if you are going to take the right part here, you have support reaction. So before that, you need to get back and determine the support reaction. Then you are going to make the cut and work on that section. So you need to make sure that whether it's necessary to determine the support reaction of the truss. Also, the third point, draw the free body diagram of that part of the section truss which has the least numbers of the forces acting on it. Assume that I have the left part and the right part here. Assume that I know the values of the support reaction. I know the value of here and here and here. Then now all the forces here are known except those. Similarly here. Then in the left part I have only one force, and in the right part I have three forces. So which one is better? The least number of the forces acting on the truss is the best option for me. So in that case, here I have three forces. It means that a lot of calculation, but here I'm going. It's required less calculation. So I'm going to choose this part. Number 4, you need to remember that if the force is pulling on a member like this one, that means I'm going to have tension in the member. So like here and here. If the force is pushing on the member like this one, that means here I have compression. The last point here, when I'm going to deal with the part, the left part or the right part, when I'm going to apply the equation of the moment, I need to take the moment about a point where I can have only one unknown. So for example here, if I'm going to take the moment about the point C, I'm going to eliminate FGC and FBC, and I'm going to end up with FGF, which is the only unknown I can easily solve for that force here. So you have to be very clever about using the that equation here. So now let's solve example so that we can connect all the discussed concept. So here it's required to determine the forces in the members GE, this one, and GC, this one here, and BC, this one here. We need to determine the forces in 3 members, 1, 2, and 3. If I'm going to use the method of joints, I need to start from here and move in there and so on. But since I can use the method of the section, I can directly make or pass a section here to reveal the internal forces acting on those 3 members. So in this case, it's better to use the method of join, the method of sections. And also it's required to tell us whether those members are in tension or in compression. So let's see how to use the method of sections in order to solve this problem. So the first step, we need to make a decision on how to cut. So we need to determine where to cut. Since it's required to know the forces in the member GE and GC and BC, it's obvious that I need to cut here at the middle. So I'm going to cut here. I'm going to pass a section here. This is the first step need to be done. Then before I separate the parts, I need to know whether it's required to know the support reaction or not. So before isolating the appropriate section, whether it's the left one or the right one, we need to know whether it's required to know the values of the support reaction or not. In that case, in order to deal with the left part, I need to know the support reaction at A. If I'm going to deal with the right part, I need to know the support reaction here. So in this problem, it's a must. I need to determine the support reactions. So I'm going to determine the support reaction. In that case, you remember how to deal with that. We need to draw the free body diagram. Here I have pin support, and here I have ruler support. Instead of the pin support, I'm going to have a reaction on Y here and reaction on X. So I have AY and AX. Instead of the ruler, I'm going to have a reaction here, dy. Now I'm in position to use the equations of equilibrium. So in this case, I'm going to start with the summation of the forces in x-axis should equal 0. And according to the sign convention, AX is going to be negative and 400 newtons is going to be positive. So this value is positive, this value is negative. The summation should be 0. Then easily I can know the value of AX, which is 400 newtons. So I know now the reaction here. Then if I'm going to use the summation of the forces in y-axis, I'm going to have two unknowns, which mean that I need to avoid this. I'm going to take the moment about a point where I can have only one unknown. So either to take it about A or about D. So here we are going to take the moment about A. Here I'm going to eliminate AX and AY. I'm going to have only dy as unknown force. Then I have that force is going to cause a moment. This one is going to cause a moment, and this one here is going to cause a moment. Regarding the dy, if I'm going to draw the line of action here, and here is the point of rotation, then the force is going to be positive, and the perpendicular distance is going to be 12. And regarding the 400 newtons, if I'm going to draw the line of action here, then this one represents the perpendicular distance 3. And it's going to be clockwise, which is negative. Regarding 1,200 newtons, the line of action here, the shortest distance is there, 8, and is going to be counterclockwise, which is negative. So I have this force is going to cause negative moment, and the perpendicular distance is 8. This one here also is going to cause a negative moment, and the perpendicular distance is 3 meters. And finally, the reaction here is going to cause positive moment, and the perpendicular distance is 12. And the summation should equal 0. Then I have only one unknown. I can easily solve for dy. dy came out to be 900 newtons. So now I know the value here. Now I'm in position to use the equation of the forces in the y-axis. So now I'm going to say that the summation of the forces in y-axis should equal 0. I have AY, which is unknown. I have dy. I found EY here, and I have 1,200 newtons. So according to sign convention, this one is positive, this one is positive, and this one is negative. I already know the value of dy. I can easily solve for AY. AY came out to be 300 newtons. So now I determined all the support reactions. Now I need to draw the free body diagram of the segments of the section truss, which has the least number of the forces acting on it. I'm going to cut here. I know the forces here, and I know the forces there. So now I need to choose either the left part or the right part. Here I have reaction, force here, force here. I have 3 forces. Here I have 2 forces. So I'm going to use the least number of forces acting on the part. So I'm going to choose the left part because I have 2 forces compared with 3 forces in the right part. I need to put the internal forces. I need to assume the direction. So here we are going to assume the force here is compression, and this one here is tension, and this one here is tension. You can assume whatever you want. Then I'm in position in order to use the equations of the equilibrium. The principle of the method of section, since the truss is in equilibrium, that means if you are going to pass any section, any part should be in equilibrium. So now I need to use the equations of the equilibrium. Again, we need to be act smartly regarding the equations of the equilibrium. Okay, so in this case, you can say that the summation of the forces in y-axis should equal 0. Then you need to decompose that force into x and into y. If you are going to apply this, you are going to know the value of FGC. So this is one method of doing it. Also, you can take the moment about a point where you have only one unknown. For example, you can take the moment about the point G. So you are going to eliminate FGE and you are going to eliminate FGC. You are going to end up with FBC. So you can take the moment here. Then that force is going to cause a moment. If this is the line of action, then it's going to be multiplied by 3 and it's going to be positive. Regarding the 400 newtons, it's going to have the same perpendicular distance, but the direction is going to be clockwise, which is negative. And here I have 300 Newton. If I'm going to draw the line of action, then the perpendicular distance is 4, and the direction is negative because 300 newtons is going to cause clockwise moment. So if I'm going to take the moment about the joint C, I'm going to have that force here is going to be negative. The perpendicular distance is 4, and also this force here is going to produce negative moment, and the perpendicular distance is 3, while the force FBC is going to cause counterclockwise moment, which is positive moment, and the perpendicular distance is 3 meters. Now I have only one unknown, which is FBC. So FBC came out to be 800 Newton, and the value came out to be positive. And here the assumption, we assume that the force is tension, and the answer came out to be positive. That means our assumption is correct. Then also you can take the moment about the point C. If you are going to take the moment about the point C, you are going to eliminate that force and that force. You can easily solve for FGE. If you are going to take the moment here, this one is going to cause positive moment and the perpendicular distance is 3. This one is going to cause nothing, and this one here is going to cause negative moment and the perpendicular distance is 8. So if I'm going to take the moment about C, I have 300 newtons negative moment, and the perpendicular distance is 8 because here is the line of action and here is the shortest distance, and FGE, here is the line of action and here is the shortest distance, 3, and the rotation is counterclockwise. So it's going to produce a positive moment. Now I have only one unknown. I can easily solve for FGE. FGE came out to be 800 newtons. We assume that FGE is causing compression, and the answer came out to be positive. That means our assumption here is correct. Then I can use the summation of the forces in y-axis. So here I have 300 newtons, this one here, and I need to decompose FGC into y. Into y, I'm going to have 3/5, and it's acting down. So I have this force and that force. I can use that formula from the beginning. Doesn't really matter. So now I have only one unknown. I can easily solve for FGC. So in the first equation, we determine FBC. In the second equation, we determine FGE. And in the last equation, we determine FGC. Here I have tension, here I have tension, and here I have compression. Now I finished from example number 1. If you have any questions regarding this example, please see example 2. So now we need to solve example 2. We have different situation here. It's required to determine the force in the members BC, here BC, and CF, and FE. So we need to know the forces acting on 3 members, this member, and this member, and that member. And also we need to state if the members are in tension or in compression. So here he didn't ask, he didn't show us which method should be used. But we know that for situation like this one, the method of section is the best method. So we are going to use the method of section in order to solve that problem. The first thing need to be done, we need to decide on how to cut the truss. So we are going to cut the truss like that from here, so that we are going to have 3 unknowns. If I'm going to have more than 3 unknowns, we are not going to be able to solve the problem. So we are going to cut here. Then we are going to have left part and right part. Then we need to decide whether we need to determine the support reaction or not. So if I'm going to ask myself that question, if I'm going to take the left part here, I need to know the support reactions. If I'm going to take the right part, in that case, I don't need to determine the support reactions. So if you are going to choose the right part, then we are going to skip the situation where it's necessary to determine the support reaction. So since we are going to take the right part here, I'm not going to determine the support reaction, and the problem is going to be more simplified. So I cut here. I need to put the internal forces, and also I need to assume whether the members are in tension or in compression. Regarding the member EF, I'm going to assume that member is in tension. And CF also, I'm going to assume that member is in tension. I'm going to assume the member CB is in compression. So here I have 3 unknowns. So I have, now I'm in position in order to choose or to use the equations of the equilibrium. All of the forces here are known for me, so no problem to use the equations of equilibrium. I can decompose that force into X and into Y. So it depends on what should I decompose that force. Here I have 4, here I have 4, which means that the angle here is 45. So I need to multiply by to get the component in X, I need to multiply by cosine 45, and the component in Y, I need to multiply by the sine 45. So here I can use the summation of the forces in y-axis equals 0. I'm going to have 600 pound, 800 pound, and I'm going to have the force FCF times sine 45, which is up, which is positive. So if I'm going to choose that equation, I need to take care of the sign convention. This one is negative, this one is negative. And here, the component of that element in the y-axis is going to be positive. So we are going to have only one unknown. I can easily solve for FCF. FCF came out to be 1,980 pound. And the answer came out to be positive. That means the assumption here is correct. The member is in tension. Then I can use the equation, which is the summation of the forces about any point should equal 0. Again, we need to be smart about that equation. We need to choose a point where we have only one unknown. So if I'm going to choose to take the moment about C, that would be great, because we are going to eliminate that force and that force and that force. I'm going to have only FEF and 800 pounds. So that will be great choice. Also, you can take the moment about F. You are going to eliminate that that force here and that force here. You are going to have moment from that force, from that member, a moment from here, and moment from that force. So let's say that we are going to take the moment about the point C. Like I say, point C is a great choice. You are going to eliminate 3 forces. So you are going to have FEF. So here's a point of rotation. Here is the line of action. The moment is going to be positive and the perpendicular distance is 4. Regarding 800 pound, here's the point of rotation. Here's the line of action. The moment is going to be negative because we are going to have counterclockwise moment. And the perpendicular distance is 4 feet. So here I have that force times 4, positive, and here I have the force here, negative times 4 also. But 4 here is this distance. I have only unknown, easily can know the value of the forces acting on the member FE. And the answer came out to be positive, which means that indeed the force acting on the member EF is in tension. Again, finally, I can take the moment about the point F here. So if I'm going to take the moment about the point F, I'm going to eliminate this one, this one. I'm going to have this one, and that one. Regarding the FBC, if I'm going to draw the line of action, then here the shortest distance is 4. So this one's going to be multiplied by 4, and it's going to be positive because it's going to cause a counterclockwise moment. 600 pound, if I'm going to draw the line of action here, then here is the perpendicular distance, which is 4. But the moment is going to be counterclockwise, which is negative. Regarding the 800 pound, if I'm going to draw the line of action here, then here is the perpendicular distance, which is 8 feet, and the moment is negative because we are going to have a clockwise rotation. So here I have FBC times 4, shortest distance here, 600, also times 4, shortest distance here, negative, 800, the shortest distance, which is here, 8, and also it's negative. Now I have only one unknown. I can easily solve for FBC. FBC came out to be 2,200 pound, and the answer came out to be positive. We assume the force here, BC, is compression, and the answer came out to be positive. It means that really that member is in compression. So the problem, it could be very easy if you can solve smartly. You know where to cut. You know which part is the best one. And again, you have to be very smart about using the equations of equilibrium. So this kind of problems, you need to be vigilant. You need to be focused so that you can finish the problem in no time. Okay, so I'm going to stop here.